Good evening, everyone. Hope that you can hear me. It's nice to see you again. As you know, I'm in my visiting period, so I'm currently in the south of France. And today I wanted to present the speaker because Laura is part of the ISSG program, so the Structural, Seismic and Geotechnical program I'm representing. And in particular, Laura started her PhD in November 2021. So she's part of the 37th cycle. So she's now in the middle of the second year, more or less. She graduated in civil engineering for risk mitigation in Lecco in October 2021. And then she started her PhD in November. She started her PhD with Professor Muchacha. So she is now involved in the structural field. And in particular, in Laura's group, there are 5 PhDs, 1 postdoc, and they are developing models, especially for like high temperatures and also high stresses, for example, after earthquakes. And their specific field is also related to life cycle assessments. And today, Laura will present us her work, in particular her models, around the hybrid concrete timber structures. And she will also talk about a particular focus on sustainability. So, Laura, the floor is yours.
Good afternoon, everyone. So first of all, thank you, Angela, and thank you, Chiara, for the presentation. So the title of my presentation today is Feedback for Hybrid Structures, an innovative perspective from numerical modeling to environmental assessment. And so there are here just a few information that Angela will give you some information. So let's get directly to the presentation. Just a brief outline of the presentation. So first of all, introduction in order to understand the main topics, and then comparative life cycle assessment analysis. So in order to compare different buildings, and then some numerical modeling, so some challenges and strategies, and finally some slide on concerning remarks and some next steps. So first of all, focusing on this figure, this represents the country workshop day for 2023. And this day represents in a country on the other hand, and natural resources for that year. So, for year 2023, this day will be July more or less. For most of the countries, Western countries, actually, that will be already happened in the first part of the year. So this is an alarming result. So what is the problem? That humanity's ecological is greater than your biocapacity. So the biocapacity deficit for basically all the Western countries. And if we focus on the building sector, this is responsible for 45% of global energy consumption, 30% of the generated waste, and 40% of the global greenhouse gas emissions. So these are some data that I think it's worth to think about. So as structural engineers, we should face some challenges. So first of all, the increasing of buildings work, then, as said in the previous slide, some sustainability that cannot be avoided, and then the performances for exceptional actions, for example, during earthquakes, like in the pictures. So, a solution that I'm studying is multi-story timber and hybrid timber building. So, this could be a valid solution. So, the main issue is the implementation of strategies to reduce buildings' environmental impact, but maintaining the structural performance, like timber hybridization. So, there are mainly 3 steps. The first one is to understand the techniques to hybridize timber with other materials. Then we need to collect studies, and as you can see in this chart, Just 20 years ago, basically, there were no researches on timber concrete concrete, for examples. And we also need comparison with traditional solutions because it's fundamental to understand the differences and the similarities. Then, concerning timber hybridization, generally it is faced in two tasks. So, timber sustainability, which is characterized by greenhouse gases, and in particular, we have the biogenic carbon content of CO2, which is a specific type of engineered wood. So we can see this is negative carbon dioxide emissions. Then we have the construction site. So concerning the construction site, there is a high level of prefabrication with, which gets much faster the construction time. And then obviously we have lighter elements. Then concerning the structural hybridization, at the element level, we can have both standard components and tailored components. This material is characterized by very high adaptability. And then finally, we have to think about the building level. So we should assemble all our parts according to required performances. So for example, we can observe the last picture, which is 10-story timber buildings, which is subjected to a specific earthquake. Then it's now important to consider the timber on its own. So we just spoken the timber as a composite, so composite with other materials, but now let's focus on timber, which is an orthotropic material, and this is a very specific characteristic because the response of the material depends on which axis is stressed. And in this case, we will have the best performances on the longitudinal direction, and on the other hand, the worst performances, for example, on the radial direction, because many discontinuities are made by the forces. So we are generally used to see this type of equation, which is generally adaptable for steel, but as we said, is orthotropic. So we should use this equation, which is a little bit more general than the isotropic one, and they have different characteristics. In particular, for isotropic material, we have 3 independent constants, and on the other hand, for the orthotropic one, we have 9 independent constants. So 3 elastic moduli, 3 Poisson's ratio, and 3 shear moduli. So concerning on the seismic behavior, it is a common belief that timber buildings behave much better compared to reinforced concrete in case of earthquake. But actually, let's observe these 2 pictures. They are 2 pictures of 2 buildings affected by the same earthquake. It was the Kobe earthquake that happened in Japan in 1995. Just to give an idea, this was characterized by a 6.9 on the moment magnitude scale, and you can see that the left building is a reinforced concrete one, and the right one is timber, and they have experienced failure with different mechanisms, but the result is the same. The building is not more visible. So it is maybe better to focus on learning of both 2 types of building. And this common belief that I mentioned before is based on the fact that timber is very flexible, and this is true, but timber actually is also brittle, so basically the failure happens without any plastic phase. So this is a big problem. And then concerning again the seismic behavior, we can see this map, which is as a map with 10% exceedance probability in 50 years, and for Europe, and we can see that the most timber buildings in Europe are located in the northern part of Europe due to traditional and historical reasons concerning timber use. And but these areas are characterized by low or even very low hazard. We have some different cases in Italy, but they are very rare, so we still need to investigate some case studies. More or less the same situation happens in America, where we have actually the tallest timber buildings in the world, which is located in Milwaukee, but you can see that it is in a very low security area. And just to give an idea, this is a 25-story building, and the 6 lower stories are reinforced concrete, and just the 19 upper ones are timber. So this is very common practice to give the adequate lateral stiffness to the whole building. So the critical aspects that we can underline are the shortage of observable data, as we mentioned in the previous slides, and then we will see the stiffness of the structural system, which is generally achieved by RC structural cores, and then we should also focus on detailing and connection. So something that in timber concrete is presented in this part of the slide, where we have the concrete slab, which is made of CLT or glulam, so different types of engineering wood. So we have now focused on the structural part. But how can we actually compute the environmental performance with the life cycle assessment analysis, which is regulated by the ISO regulation? And life cycle assessment studies all the phases of a building, generally product, but we are focusing now on buildings. So we have stage A, which focuses on product and construction phases. Then we have stage, so then all the parts, maintenance, repair, replacement, and also energy and water use. Then we have the end of life, so what happens to the materials at the end of life of the building. And then we have the stage D, which is actually not mandatory, but is fundamental if you consider in particular buildings, because just in this way reuse and recycling are counted. Then, as we said, timber is a highly recyclable material, and we have different scenarios. In particular, the first two are reuse and recycle. So reuse is simply, actually not simply, but keeping the members and using them for other structures. Then recycling, we keep the members, we make sheets, and then we make other members. Then there is incineration, and then landfill. So we can see the differences. Actually, in the first two cases, the two stages, so C and D, are balanced. But if we consider landfill, we do not have any advantages for timber use. So these are different scenarios. Then I just would like to focus on the special case. So the timber presented in these two pictures comes from trees demolished by a boom storm characterized by very strong wind that affected the region in autumn 2018. And in particular, in the upper picture, we can observe two buildings dedicated to social housing with the CLT made with these trees. Then in the lower part, we can observe a structural work, which is obviously not something structural, but I would like to think this as a special case of life cycle thinking, where actually all the previous stages are skipped and we are directly linked to the recycling. So, focusing again on the sustainability, I've made a research on the state-of-the-art review on comparative life cycle assessment on timber and reinforced multi-story buildings that ended in a publication on a conference paper. And this research was characterized by a two-step methodology. The first one was the collection of data, so basically of paper with comparison of these two types of building, and then these data were analyzed, and the results were on critical phases. So such phases characterized with uncertainties, so not standardized weights, for example, and significant weights. So this leads to this summary chart where we can observe that phase B is always very impactful and it rules all the life cycle assessment, both in reinforced concrete and both in mass timber or timber hybrid cases. But we can also see that considering cradle to cradle analysis, so considering also the laboratory phase D, we have several advantages for the exploitation of this phase. Then we can skip to the case study. So we have this case study characterized by this plan, and this is a building located in Milan. This is a region characterized by a low moderate seismicity, and this is a residential building with 8 floors. So we can observe on the lower part of the page, on the left part, the original implant layout characterized by RC structural cores, and on the right part, the alternative solution with CLT shear walls. Then, so mainly 3 solutions were suggested. The first one is the traditional one, so the reinforced concrete solution, where everything was made by concrete. Then we have the 2 hybrid solutions. The first one, which is H, is characterized by steel columns and steel beams, and then walls and floor panels. Then the W solution, which is something between H and RC, which is characterized by steel columns and beams, floor panels, and reinforced concrete walls. So just to compare 3 solutions. So considering the hybrid solutions, just steel quantities from the bill of material was inserted in the Athena impact estimator for buildings, which is a software that, according to international standards, carry out the life cycle assessment analysis. Then, to this data, the data, so the environmental product declaration data were added, and then the data concerning carbon dioxide emission were calculated. More or less the same was done for the RC solution, but in this case, all quantities were inserted in the software. Then, first of all, different end-of-life scenarios were considered. So, for traditional solution, no end-of-life scenario was considered, so just a cradle-to-grave, as it is commonly done. And then we have 5 hybrid solutions. So the first one is reuse, then recycle, then landfill, in order to see what happens if I do not recycle timber. Then the first one is something like a real case solution, because generally it is very difficult to reuse all the timber. So a part of this is incinerated. And then we have a 5th solution, which is the same end-of-life scenario, fourth one, but we have no replanting hypothesis. So this is an incorrect forest management. And also, we will see which are the differences. Skipping to the actual results, we can focus on some sensitivity analysis. So, considering CLT, we have the transportation phase, which should be accounted. And in this case, we can observe some distances according to some common distinction, and in order to be on the conservative side, we consider the data highlighted with the Then, considering stage D, we can notice that stage D in literature is neglected because it is cumbersome to be computed. So, in our analysis, it was first disregarded, then it was computed. So, according to common values collected from literature, it was evaluated the percentage of the total impact, and then 2 scenarios were suggested. The first one is a low energy efficiency scenario with a stage D, which has a much greater weight, and then we have a high energy efficiency, which are lower weight. Then, concerning again sensitivity analysis, we have this calculation concerning the volumes of steel quantities in terms of connections, and we can see that just from a quantitative point of view, they are negligible. Obviously, they cannot be considered negligible a general, because they are very important to guarantee all the performance of the building. Then we can skip to the results. Actually, we can see that the hybrid building width is more or less 1/3 of the reinforced concrete one, and for the reinforced concrete, the amount is due to the slabs. Then we can pass to the results concerning the life cycle assessment analysis, where in these cases the results are grouped by assembly groups, and we can see that both for reinforced concrete but also for hybrid solutions, the flows have been in one case negative and the other one is positive. We can also focus on H5, where we can see that the correct forest management has a very strong weight. Then, in this slide, it is possible to compare cradle to cradle cycle assessment analysis, and we can see here the advantages of considering stage 3. Then, in this slide, we introduced the stage B, and we can see the differences between a high efficiency building and low efficiency building, in particular, focusing on these two data. That for H4 case, the weight is 30% of the RCQs. So very strong reduction is acknowledged. Then just a final comparison considering life cycle assessment. Here we can compare cradle to cradle, considering one cubic material, and we can see that actually we consider no replanting and with a real case study end of life scenario, and concrete with a bit of recycling. So considering these two cases, actually the results are not so different. Actually, the differences come from correct management, both at the end, but also concerning force management. Then we can see through the numerical modeling, we consider this case as a benchmark analysis, where there is this beam to column initially considered just a part, and then this lab panel was added, and in particular different type of connections concerning the connection of the CLT slab were considered. In particular, this is the layout of the test, where this structure is subjected to a complementary moment, and in particular we have different elements. The first one is just linked with steel, while the other ones are linked to timber, and it's possible to observe that mainly timber is characterized by crushing close to walls, or even also the lamination at the mode 9. So these are the main units. So this is the full part of how I organize the analysis. So the first one is the strip joint calibration, so just steel. Then timber orthotropic behavior modeling. As we said, timber is orthotropic, so it should be adequately treated. And then we have the push-up test calibration, and then finally there is steel timber joint calibration. I will just focus on the first three steps, as the fourth one is still important. So I will focus more on some strategies and methodological choices, because I think this is the most interesting part. And so this is simply some measures, some values, and after calibration, we obtain this score. So this is our starting point for the analysis. Then timber orthotropic modeling, where there is these 3 points when you test from literature, and there are these lamellae, and actually the most important step was the orientation of the axis. As we said again, timber is orthotropic, so in this case we put these values directly from literature in order to reply this test. What we observed from literature is that it is not so common to find all 9 constants present always in the paper. So it was conducted a little research in order to understand some common values which are represented in the charts in the right part of the page. And so the variability of some values are highlighted, and in the table the averages are listed. Considering this sensitivity analysis, this was applied to the CLT panel that was mentioned in the previous slide. So we have the first one, so timber one reference, which consider value directly from literature, and then different cases, calibrated values we consider. And the result is that the results are very, very, very similar. So we can consider these percentages as for other cases, for other types of tests. Then we can see here normal stress and shear stress distribution along these three lines, and these are correct as they are similar to literature, to what literature presents. And then we can see the last part, which is the push-up test calibration. So the steel beam is pushed down, and then there are different modes. So one is just timber crushing. Then we have the one plastic hinge creation concerning screw, and this was the case testing. And then there is this ultimate case with the two plastic hinges creation. And in these cases, two modeling techniques were employed. In particular, the first one was testing with Athena Cervetta, and in this case, the screw was not physically modeled, but it was modeled like a smear screw, so with a user-defined interface behavior. And this was the result, so this was a valid approach. And then we have the second approach, which was in Abacus, and in this case, we modeled the coach screw physically, but generally applied. And then we have here problems, we can say, of contacts. So concerning normal contacts, simply hard contact was applied, and concerning tangential behavior, the penalty approach with different friction coefficient to simulate the rope effect of screws concerning timber contact was applied, and in this case the result was satisfying. Then, just a few comparisons between the experimental results from the literature and my results. So here we can see from the literature this plastic screw, and it is visible also in the coach screw. And then, again, for timber, it is very important to identify the crushing zones where the overcome of the strength happen, which in Italian is rifollamento. And so we can see that it is also properly modeled also in the Abacus model. So just to conclude, just a summary slide. So if I empower this sustainability of single buildings with a wise use of material, with a forward-looking perspective, so by imagining the stage D, actually also during the design stage of the building, and considering strategies to facilitate reuse and recycling as shown in this picture. For example, there are some demountable screws which help to reuse and recycle the material. And then considering also analysis on other scales, so parametric structural analysis to consider different combination of materials, so different members. So it is possible to arrive to the last step, so the characterization, the assessment of a parameter to measure in the same time structural performance and sustainability. But this is just a next step. So in this way, with this flow chart, we can arrive to the sustainability of the whole system. So the presentation is almost finished. I just would like to focus on a more philosophical issue. I would like to underline that this is not the solution, this is just a solution, because many solutions, and in order to communicate you this concept, I'd like to use the of a great Italian mathematician, which says that we cannot assume just absolute truth, because otherwise we lost all the points of view. So this is just to represent my idea of the research. So thank you for your attention.